There we go. Sorry about that. False start there. So here we go. Today we have Dr. Francois Tissot talking to us. He is an isotope geo and cosmochemist who, with his group, applies isotope systems including zirconium, iron, chromium, vanadium, uranium, and calcium. His work has been very diverse from the earliest solids to deep sea corals to biomedical and archaeological applications. Francois's deep time focuses are closely tied to the formation and evolution of the solar system, the reconstruction of paleoredox conditions in the ocean atmosphere system, and the potential of non-traditional stable isotopes for studying magmatic processes as well. Recent accomplishments include helping to establish uranium isotopes as robust tracers of oxygen levels and detecting unambiguously 247 curium in the early solar system. So Francois received his engineering degree from École nationale supérieure de géologie in Nancy, France, and his master's in sanitary engineering from Luleå University of Technology. Consequently, he went to do his PhD at the University of Chicago, where he worked with Dr. Nicolas Dauphin, developing double spike uranium isotope analysis and applying to igneous and paleoceanographic contexts. After his PhD, Francois was the W.O. Crosby postdoctoral fellow at MIT, where he worked on angrite petrogenesis. Consequently, Francois became a professor of geochemistry at Caltech, where he has established a very strong lab, Isotoparium, with students working on the isotopic composition of natural materials of all nature. Please take it away, Francois.
Thank you so much for this great introduction. Hi, everyone. I don't think I've met many of you, so this is a nice opportunity, and I'm happy to give it my best shot to interest you in something we've been working on these last few years. The title says what we're going to claim in the end, oxidized Hadean magmas and Archean onset of mobile plate tectonics using uranium XANES in Jack-Hill zircons. So there's a lot of concepts and terms in there that I'm going to explain. Before that, I don't know if it's customary, but I would really like if people jump in and ask questions during the talk. Otherwise, it really feels like I'm talking to myself for an hour. So don't hesitate to interrupt. All right, so typically when I have a title that has uranium and redox concepts in it, I'm going to talk about something like the uranium isotope proxy, which is what I worked on during my thesis. It's a proxy that has been developed that leverages the fact that oxidized and reduced uranium, when they exchange at equilibrium because of the nuclear volume effect, there's an isotopic fractionation that is very large, actually 1.2 per mil. And so if you look at a uranium budget, which is depicted here, the uranium will go from the crust to the rivers almost unfractionated, but then once it gets to the ocean and it gets stripped out of the ocean, particularly in anoxic environment and euxinic environment, like black shales, there's going to be a very large fractionation towards heavy. So the shales are typically very heavy. And that makes the seawater composition slightly light compared to the crust. And how light the seawater composition is can be used to quantify the amount of anoxia. So on this plot on the right, you see delta 238 uranium on the y-axis versus F anoxic. F anoxic is either when it's a little f, it's the extent of seafloor anoxia. When it's a big F, it's the amount of uranium in black shales relative to the entire uranium pool. And you can have essentially an injective function that gives you, for any delta 238 value, an extent of anoxia. And this has been used to, assuming you can get the seawater value in the past, which you can get from carbonates or shales with some assumptions, you can reconstruct redox condition in the ocean. I'm going to just show you one example, but there has been many studies, for instance, in the Cambrian to today, looking, and those are not my studies, by the way, and this is everyone in the community looking at outcrops, identifying where important transitions were, and then measuring uranium isotopes. The part of the work that is ours from my postdoc, Mike Kipp, is the red line, which is the fit that an inverse model that we put forward is giving. And the advantage of doing the same inverse modeling on all of those data sets is that you can then get consistent quantification of anoxia across all studies. And so this has proven very powerful. And typically, this would be what I would be talking about. And I would be tell you something like, oh, this is a very exciting proxy. Look at all the papers that have been written on uranium through time. This is what this plot shows. Number of papers on the y-axis, the years, starting in 1930 with the seminal paper by Alfred Neer. And you would see here the different fields being represented: nuclear forensic, early solar system. If I add the paleoredox use of uranium isotopes, this would be the blue curve that I just added onto the plot. And you can see that after the initial report of redox-driven variation in 2007, and the first application of the system in 2010, there has been an absolutely exponential increase in the number of studies looking at uranium isotopes for paleoredox applications. It's actually so much that it's kind of hard to keep track of. So to help the community, we've created a database, a uranium isotope database. This is the work one of my students did, Hao Yu Li. And first we released it as a big Excel file, which no one likes to have to dive into. So to make it easier now, we've launched a website where you can sort through and just click your way through the data set that you are interested in. The website is live. It's the uidb.caltech.edu. So if you go there right now and you click, you can go from terrestrial samples, and then you can choose your sample type, sedimentary rocks. You can choose the eon or the period and narrow down, and it will give you all the papers and all the data from corresponding to the selection you've made. So with that being said, I promised I would not talk too much about uranium isotopes, but it is the foundational or the motivational question behind the work I'm going to present. So I'm going to explain that part, and then we'll dive into the real talk. So about 5 years ago, I suppose, we had been making the observation with my close colleague Mauricio Ibanez Mejia that there was a lot of uranium isotope variation in zircons. Those are the points right here. The red zircons are pooled fractions. So you take a rock, you extract the zircons from that one rock, but then you put all the zircons together. This is what that data shows. The blue zircons, I'll talk about a bit later. This is a single zircon grain analyzed by myself and also showing quite a bit of variation. When I say quite a bit, for comparison, I've also plotted fresh basalts, OIBs, arc lavas, and differentiated crustal rocks. And you can see that the level of spread in pooled and single zircons is very similar to differentiated crustal rocks. And so some of the studies that have been looking at those differentiated crustal rocks have hypothesized the impact of metamorphism and fluid circulation, but also redox processes. And the question that we were trying to answer was, what is the origin of those uranium isotope variation in zircons? And could it say something about the redox of the sample, which obviously would be very nice if it was the case, because then we could use those zircons to go probe the very early Earth status, where all we have is zircons. So this was the starting observation and starting question, and we designed a workflow which I'm going to call the unstoppable workflow, because it will allow me to make a pun in a few slides. But basically, we said we're going to look at a series of rocks, and we're going to characterize them very well. We are going to make a thin section, look at it under the PMA to get the FO2, and then we're going to do some mineral separations, extract zircon, titanite, and other uranium-bearing phases. And then we're going to very methodically go through that. So we're going to make mounts with 50 grains for each sample. And then there is a funneling of characterization that happens where we would use SEM, cathodoluminescence, EBDSM to look at the compositional zoning and the crystal orientation. We take a subset of 20 grains. We do micro Raman to look at radiation damage because we want to make sure that we're not looking at grains that are destroyed. We take an extra step in the funneling. We take 10 grains, we go to the SIMS, we do trace element, titanium thermometry, oxygen isotope composition, uranium lead, all of that. And then the final step, we were thinking we would take 5 grains and go to the synchrotron, specifically the advanced photon source at argon. And there we would do the uranium valence inside the zircons and the bonding environment to try to see really what is controlling the isotopic fractionation. And this is all context because the greater project was the rest of that workflow, which is here, where we would measure uranium isotopes and compare the uranium isotope of individual grains to the rock that they come from. And we were very excited about this. When I say we, Mauricio and I were working on this proposal, and we submitted to NSF for a career. And of course, and this was objective 2 of the proposal. And of course, 224 days later, the proposal got rejected, which is always unsurprising, but we got some nice weaknesses outlined. The first one, which I've outlined here, is it would have been helpful if the proposed technique developments were completed. I would agree that would have been nice if all the work had been done, for sure. That's always true. The second one here is preliminary data from the ZANES would have been helpful to demonstrate the potential of the method. And as frustrating as it is to hear, it's a fair comment. We had not demonstrated that it would work. We knew that it could be doable, that people do ZANES to probe the speciation of uranium in materials, but we had not shown that it could be done on single zircon grain the way we wanted. So we took it to heart and we went to APS. Here's a photo of the synchrotron at Argonne. We reached out to 2 of our colleagues there, Matt Neville and Tony Lanzarotti. And if we look at what APS does, it does almost everything from biological science to earth science, physics. Specifically, we worked at the beamline 13 IDE, where they're beautifully set up to do uranium speciation. And when I say we went to APS, actually, we never went physically because they are so well equipped and set up for remote work that you can do that from your office or anywhere as long as you have an internet connection. So we went there and we did some ZANES. So what is ZANES? ZANES is a method that uses X-rays to probe the crystal lattice and the electronic structure. You fire the X-ray at the sample, you scan over a range of energy, and when you get to the energy where the inner electron is going to get excited, there is an increase in the absorption from the sample. So you are looking for a sharp increase in absorption of the X-ray. And that increase of absorption depends on the oxidation state of the species you're looking at. Because if something is more oxidized, it requires more energy for the electron to be excited. So as oxidation state increases and you're scanning the range in energy, you will see the shift in the peak position of maximum absorption. Here's an example on the right where you see the difference between the europium-2 peak and the europium-3 plus peak in standards and in glasses. This is showing just one very well-known example. So you can do the same thing for uranium. And we went and we did that on 2 specific samples. The first one is FC1, which is a sample from the Duluth gabbro. It's an orthosite. It's been well characterized. The FO2 of the rock is about the quartz-phyllite magnetite buffer. so relatively reduced by comparison to the next sample, which is FCT, which is the Fish Canyon Tuff volcanic rock, which has a log FO2 of QFM plus 2.5. So a very significant difference between the two rocks. And sure enough, when we do the ZANES, which is presented here in this figure, you can see that there is a difference in the maximum intensity of the absorption. Here we're looking on the what's called the uranium L3 edge, which L is referring to the position of the electron that's being probed. And I've put as gray bars, gray arrows, I guess, the position of the uranium, pure uranium 4 plus peak and pure uranium 6 plus peak. So you can see that FC1 is essentially entirely uranium 4 plus if we trust this preliminary measurement, and the Fish Canyon is about 50-50 4 plus 6 plus if we trust that this is a linear interpolation we can do. We see this on the uranium L3 edge. We see it also on the M4 edge. So the L3 edge is measured at 17 keV. The M4 edge is measured at 3.7 keV. There is less intensity on the M4 edge, but the data is still very reproducible. And what's nice is the peak position between 4 plus and 6 plus there's more space between the two peaks. So the M4 edge is actually a much nicer place to measure at. And this is what most of the data that I'm going to show you was measured at. So we did these measurements. We're lucky enough to get a preliminary session at APS, and all the data was consistent across all the grains. We thought that should be enough for the proposal. Let's try to resubmit. So we will go back to the unstoppable workflow we had. We add the preliminary ZANES data, and this time around the proposal went through, which we were thrilled. And today I'm going to tell you about this, except I'm not going to be able to tell you about all the isotopic work because we haven't done any of it yet. Because for the last 4 years, we've been stuck on the synchrotron work. So what should have been only measuring 5 samples per grain, 5 grains per samples, turned out to be the most interesting part of the work so far. We've measured hundreds of grains and many hundreds of spectra, and I'm gonna tell you why. So yeah, wait, what? We're gonna spend 4 years on just the synchrotron? Yes, because I'm gonna tell you about something that is now what we call uranium in zircon oxybarometry. So it's a very stoppable workflow in the end. So what did we do? We took a bunch of samples, which I'm going to discuss in a little bit, well-characterized sample covering a range of FO2 conditions. And we followed the workflow for the most part in terms of characterization. So we did BSC to get the composition and anything that could orient our approach to making the measurements. Are there cracks? Are there ablation spots? Things we need to avoid. We did cathodoluminescence to get to know if there was any zoning, either from growth of the zircon or from metamorphic reworking, any secondary process. And then once at the synchrotron, we also do a micro XRF map. And this is very useful because you can see it here. Sometimes you can detect, or always you can detect, but if there is a subsurface inclusion, for instance, titanium-rich inclusions here, you will be able to see them and you'll be able to avoid them when you do your measurements so that you really probe the zircon and not the inclusion in the zircon. So typically for each grain, we measure anywhere from 1 to 3 spots. It depends how homogeneous the grain is looking in CL and in micro XRF. And then for each spot, we measure 1 to 3 spectrum, depending on the uranium concentration. If there's a lot of uranium, the spectrum is going to come back and be beautiful from one measurement only. If there is very little uranium, we have to measure more times. And we get something like this. So those are all the spectra, not all the spectra, sorry. Those are all the grains we measured for FC1 in a paper that was published by Shane Auchin. And I will get back to that, but I can mention here already all the work I'm presenting is the work of my student Shane, who's been doing a beautiful job. So here's FC1, all the grains we measured. Each line that you see here is the average of the multiple spectra we've taken on the same spot. So, and I've put the uranium 4 plus and the uranium 6 plus lines, and in between I've put the uranium 5 plus line. So this is one sample, we get that much information. We've done that for many samples, and we'll go through them later. But as you can see, the amount of data can become quite overwhelming if you just have to look at spectra. So we'll find also a better way to represent it. Already what you can notice, even with this much information being displayed at once, is very often from a single rock sample, all the grains look the same. They have consistent maximum absorption energy, which is called a white line. So they have consistent white line, which means consistent redox speciation, uranium speciation. There is clear difference between some of the rocks. FC1 here is much closer to the uranium 4 plus. When you look at the samples on the top here, which are Bishop Tuff, things like this, you are almost at the pure 6 plus and member. And sometimes, if we look, for instance, at this Hidden Lake mafic complex, you see an evolution. There is a trend within a suite of samples, which represents the evolution of the redox during the evolution of the magma. So let's try to look at these data in a bit more friendly of a manner. We're going to look at the white line energy, the peak absorption energy, and just plot that against the sample type. This is what we're doing here. So the x-axis now is the white line energy of the uranium M4 edge. And then all the samples are just characterized. So this is, I guess, very adequately a Caltech plot, something against nothing. We have organized by sample type, though. So there are zircons here from volcanic rocks, from ARCs, zircons here from SPGs, sedimentary sedimentary rocks, anorthosite, and then apatite, badellite. We looked at some other accessory minerals, but the bulk of the story is going to be on zircon. The main thing that I want you to notice here is how much spread there is in the data between rocks. It goes from titanite recording only pure uranium 4 plus composition to the Lassen King Creek recording all the way to uranium pure 6 plus. Volcanic rocks are much more oxidized in their uranium and zircon than, say, for instance, FC1. But in detail, FC1 is not pure 4 plus, unlike what our preliminary measurement showed. And that's because our preliminary measurement did not have a pure uranium 4 plus standard measured at the same time. Now we have measured such a standard, and so we can calibrate exactly how things look. As I mentioned, in some complexes, in some sample suites, you have an evolution from reduced to oxidized or oxidized to reduced. If you have some time constraint, you can figure it out. But overall, most of the sample, even suites of samples, have quite homogeneous compositions. Now, of course, the question is, we're measuring all of those signatures. Are those primary signatures or are they overprinted during the lifetime of the sample? So we did an extensive amount of testing to get to be able to claim that this was primary or not, just to figure it out. The first immediate idea that systematic biases that might come to mind is that you're measuring multiple spectra in the same spot when there is not too much uranium. Maybe you're damaging the sample when you do this. Those are very high energy X-rays. It would be completely reasonable to assume that there is some damage. So we did some testing and we measured repeatedly on the same position. I'm showing you two examples. and we looked and compared the spectra, and we saw no modification of the spectra as we increase the number of repeat measurements. So beam damage does not seem to be a concern under the analytical conditions that we use. The second one, of course, is crystallographic orientation, a very well-known potential bias. So we did systematic testing where looking at Fish Canyon tuff, Bishop tuff, and Extol, we changed the orientation. We mounted the grain in specific orientation. You can see this here, perpendicular to the C-axis or parallel to the C-axis. And then in those orientation, we also rotated the mount 0 degrees, 45 degrees, 90 degrees. So we're really trying the X and Y direction to see if it has an impact. The results are shown here in the bottom panel. There might be some very slight variation, but they are not resolvable at the precision of the measurement, which is extremely good, by the way. We'll get to see in the later slides how good the quantification of FO2 is. So crystallographic orientation and grain orientation does not seem to have an impact either. Okay, next one, we have, of course, radiation damage. You're looking at zircons, they're uranium rich. Some of them will be very old. There will be a lot of radiation damage potentially. So here, this is a plot showing on the x-axis, the average uranium speciation from 4+ to 6+. On the y-axis, we're looking at the width of the Raman band, which is a proxy for the radiation damage dose. And when you go to higher values, the radiation damage increases. You can see that any of the grains that are considered completely undamaged, purely crystalline, these range from 6+ to 4+. They cover the entire range of FO2. So just from these grains alone, we could make some very strong inferences on the amount of uranium 4+ to 6+ in the samples. You can see that as radiation damage increases, but let's look at FC1 first, this light blue, it's just a vertical rise. There is absolutely no trend in any direction. There's no change in the uranium speciation that we measure as a function of radiation damage. Yes. And so there doesn't seem to be an impact from radiation damage to the uranium speciation measurement. One may maybe point to this sample, the Hidden Lakes sample, that have a very, very slight negative trend where samples get more reduced apparently as radiation damage increase. That's a possibility. So we went and we explored that a bit further. Here are those samples again, plotting the uranium white line energy against the uranium concentration. What we see is that there is a correlation for this particular suite of samples where as the samples have more uranium and therefore more radiation damage, they also have more reduced uranium. But the causality, making a claim about causality here is very difficult because the cumulates could have more uranium just by virtue of having formed under more reducing conditions, where uranium 4+ is partitioned more into the zircon. So just from those samples, it's difficult to say something. We did look at all of the samples we had for which we had uranium concentration and uranium and ZANES data. We see no systematic trend here. In fact, the samples that have the highest uranium content are also the more oxidized. And if anything, radiation damage would tend to reduce the, yes, we would expect reduced uranium when there is increased uranium because uranium 4+ partitions more readily into zircons. So there might be some slight effect here that we cannot fully tease out, but this is going to be a secondary order correction at best. We don't think it influences our results. And then, of course, we check the reproducibility because we go to APS by sessions of 3 days, which are quite intense sessions, even if we don't go physically. And we want to make sure that when we measure in March 2021 or September 2021 or March 2023, when we measure the same sample, we get the same result. And the data is extremely reproducible. Those are FC1 grains, not even the same grain, different grains from FC1 measured in those sessions. And you can see that it is impossible to tell which session is which. All the data is always the same. If you take the average for each session, you get always a very, very tight constraint on the white line energy, which means that the setup is stable. It also means that FC1 is a fantastic standard, which we recommend anyone applying this technique uses. All right, so what did we do with this? What we did is we selected a series of rocks with well-characterized oxygen fugacity, and we measured their uranium XANES, uranium 4 plus to 6 plus ratio. And this is what we obtained. We obtained a very clear correlation between the white line energy in the zircons from these rocks. And these rocks are here. If you're curious, you can also check the paper. But for once, I'm breaking the rule of not having a table in a slide. We looked at a series of rocks with well-characterized FO2 systematics. And you can see that there's this clear correlation. The biggest uncertainty on that correlation comes from the FO2 constraints themselves, which most of the methods that have been used have plus or minus 1 to 1.5 log units. So this introduces some uncertainty. Our white line energies are typically very well constrained, except for a couple of samples where either uranium content was very low or there is variability within the rocks, which would indicate some evolution of the sample. Nevertheless, so if you look at this trend, you can fit a linear trend through it, and you can relate the delta FMQ, so how far are you from the FMQ buffer, by looking at the white line energy of any zircon, comparing it to the white line energy of a zircon that would be at QFM, and divide by the slope. This is the general equation you would want to use. Specifically at APS with FC1 as a standard, this equation takes this form. This is the energy measured for the FC1 grain at which is at FMQ buffer. This is the slope of the regression of the on the left, and this is the uncertainty. So our method comes with a plus or minus 1 log unit uncertainty, which we will see later is a very good, very precise, gives very precise data. However, you may also be able, I don't know, I'm not aware of a method to do this, but maybe there is a method to also just gain insight into how much uranium 4 plus or 6 plus there is in a sample without using the synchrotron. You can still use the calibration we have created here with this data set by just using this equation here. It's all in the paper. The average uranium speciation can be used to calculate the delta FMQ. All right, now what do we do with this technique? Well, one thing, for instance, is you can probe intra-grain variability. So we're looking here at the Fish Canyon Tuff 2 zircons. They have beautiful zoning in CL images. You can see the igneous grain, the core inside, the rim outside. There's a progression. We've put on these 2 grains 3 spots, A, B, C, moving from the core to the rim. And when you look at their spectra, sure enough, there is a drift in the peak energy, and you can see an a reduction of the redox going from core to rim. This is because the very high spatial resolution of the technique allows us to probe this. Here's another way to plot this data. We're looking on the x-axis as at some distance from the center of the grain, and on the y-axis at the average speciation of uranium. Some grains like FC1 are completely homogeneous. There is no change with distance from the core. Some grains, like the grains from Fish Canyon, on average, show a trend. For Fish Canyon, we are hypothesizing that this is magma degassing that we are looking at, going from more oxidized near the core to more reduced near the rim. All right, so let's summarize a bit everything I've been telling you, which is a very intense method development, all of which is summarized in Shane's paper from last year. We've used uranium XANES to probe oxidation states in zircon and accessory phases. We've shown unambiguously that zircon do incorporate multivalent uranium. There is no significant impact of any of the potential biases that we were able to test for. And importantly, we find that there's a clear correlation between the uranium oxidation state in zircons and the parental magma FO2. So we have an oxybarometer now that we can use. And because the technique has such higher spatial resolution, then we can probe inside grains. Of course, when you have a new technique that you can apply to zircons, what are you going to apply it to? You're going to apply it to Hadean zircons because this is where most of the questions remain. So let's talk about the Hadean a little bit. I'm taking this contrast between the typical but old-fashioned idea of Hadean hell and what I would call a much more evidence-based Hadean for a lot of which looks like the modern essentially. For a good summary of what the Hadean Earth looked like, you can read Mark Harrison's book, not paper. All of this is derived from zircons. Those are the only lithic witness we have to interrogate. And so what do they say? Well, again, there's an immense amount of information in Mark's book. I'm not going to summarize his book. I'm going to give you two things that are related to uranium in zircons, Hadean zircons. The first one is actually isotopes. We're going to go back to this because it provides us some constraints. So here is the context. You have on the x-axis the uranium isotopic composition. The gray vertical band is the average crust composition that we have measured in the modern. And those blue and red areas outline expected signatures. So if there was, for instance, redox going on, redox equilibration of uranium going on at the surface of the Earth, like there is today, you would see the same kind of signatures as you see in black shales, heavy uranium isotope, up to a couple of per mil. If there were nuclear reactors, like the OCLO reactors, that would burn up a lot of the 235 uranium naturally, because in the Hadean, 235 uranium was much more abundant and above the threshold for self-sustained nuclear reactions, then nuclear burnup would bring you to exceedingly high values, all the way to 238 over 235 uranium of 200. So this is what, if you were to measure zircon grains, what you would use to interpret the signatures. Now, if I add the zircon data that we measured back in 2019 with Mauricio and some other colleagues, it's right there, the tiny plot here. So let me zoom in. Here we go. The gray band is still the crust. The blue points are zircons, 20-ish zircons that we were able to measure each individually, which might not sound like it's incredibly difficult, but I can assure you that it is. Most people claimed until we did it that it was not possible to do, to measure a single zircon for 238, 235 uranium. And what you can see is that we are very far from nuclear burnup. There is no evidence for nuclear burnup. We're not even reaching anything that looks remotely redox related in terms of uranium isotopic composition. And from that first study we did back in 2019, obviously we said that there was no evidence for widespread nuclear reactors on early Earth, which we didn't think there was, but some people have claimed. So it was good to put that to rest. And also there the data was completely in line with indicators of low atmospheric FO2. We see no signatures that would be inherited from sediments, reduced sediments, or sediments that have seen a uranium cycle in the ocean, I should say. Okay, so let's go back to now our ZANES measurement. Let's and ask the question, what are the previous views on magma redox in the Hadean? I think the most famous constraint to this day is the work of Dustin Trail using cerium anomaly-based proxy in zircons, calibrated in zircons. And this is a figure from his 2011 Nature paper, which shows that the Hadean magmas were around the FMQ buffer, and this is the value that they argue for in the paper, with the caveat that it is plus or minus 4 log units. So an average good constraint, but in terms of precision, a little bit uncertain. How uncertain? Well, just for context, here is a summary of the redox measurements that have been made on all the terrestrial planets that we have samples from. So lots of samples from the Earth here, going from Morbs to peridotite, some lunar samples here, some Martian meteorites, and expected values based on remote sensing and the landers on Venus and Mercury. Now let's put the window of FO2 that the zircons allow for the early Earth, and it's here. Basically, the constraints is that it could be any condition that has been documented in any rock on Earth or Mars, essentially. So not the tightest constraint. And we are asking, can we learn more from the uranium oxybarometer that we just developed? So we looked at Jack Hill zircons, and initially we wanted to look only at cores, but as we were going through many of the mounts that Mark Harrison provided us, we started to notice those very bright rims in CL images. Beautiful rims, clearly secondary. That's not just the initial growth of the sample. So we started to probe these as well because we have the spatial resolution to do this. So we looked in the end at 34 cores and 16 rims, and we did everything on them, everything we could. Raman for the radiation damage, uranium lead dating for the ages, trace elements, SIMS to get the thermometry and some pressure estimate, and ZANES to get the FO2. And I want to emphasize the rims, I'm going to call them metamorphic rims. I'm showing you a comparison here of what our rims look like on the left and what rims, metamorphic rims look like from this review paper from Rubato in 2017. Our rims look more like the ones that I've put a yellow outline around. So things like high pressure temperature, metamorphism, eclogites, granulites, things like that. Morphologically, the rims definitely are metamorphic in origin, and they would point to some high pressure environment. Okay, so let's look at the results from the ZANES. On the left, I'm showing you the spectra all stacked up. The main thing I want to show you is that they all look the same when you look at a specific group. So the cores all look the same, and then the rims split into two groups, which I'm showing also on panel C here. So again, the cores all look the same FO2, close to FMQ. The rims, some rims are very oxidized, FMQ plus 2.5. Some rims are similarly oxidized, but almost a billion year younger. And some rims are actually not that oxidized, pretty close to FMQ right here. So we split, just from those results, we split the rims into two groups. We split them into high FO2 and low FO2, and you will see why that makes sense in a little bit. The cores are all reduced, and the rims are either high or low FO2. In all cases, the data is extremely tightly distributed within one log unit. And this is really important to see because I'm going to now compare the data we obtained on those grains to other models that have been proposed. So if we use, instead of our uranium ZANES proxy, if we use the LAUX proxy, which uses trace elements, uranium, titanium, and is in some calibration, here's what we would have seen. We would have seen on the exact same grains some spread of 2 log units in the cores, some spread of 2 to 3 log units in the younger cores and the younger rims. And most importantly, we would not have seen any difference between the cores and the rims. We've lost already all systematic. It looks bad, but it's actually not that bad. If we compare to the other famous proxy, the one from Trail and the cerium anomaly-based proxy, it's even worse. Now the data is covering 10 log units of FO2, even going below the iron vestite buffer, which would make no sense. There would be no FeO left in the melt. And the relationship between the cores and the rims is inverted. Now the rims look much more reduced than the cores. So obviously, I'm showing this in a bit of a provocative manner. I need to say those trace element barometers have not been calibrated at metamorphic conditions, so it's not really fair to apply them to the rims. But even if we focus on the cores, where they should be completely relevant, the constraints that we obtain are very dilute. There is a lot of spread in the uranium speciation, or sorry, in the FO2 constraint. So based on that, I'm going to argue that the uranium ZANES is both more precise and much more accurate, and gives us within 1 log unit values that we can trust. Now, we also looked at the trace element content, as I mentioned, and here what's very interesting is that the grouping that we observe when we just look at the redox, just look at the ZANES, the high FO2 and the low FO2, we also see a very clear systematic difference between the rare earth element patterns of those 2 groups. So the FO2 grouping could have been seen independently from just the rare earth element grouping. On the top, here's the high FO2 grouping. In yellow, the yellow field is what a granulite would look like. The cores is the blue field in the back. The low FO2 rims are the lines here, and you can see that they overlap very nicely with high pressured gneiss or jadeite type metamorphic phases. So we have metamorphic rims, we have igneous cores. What type of metamorphism can we infer from metamorphic condition can we infer from the rim, the data we have on the rim? We have europium anomaly and titanium. From titanium, we can get temperature estimates, of course. This is the famous calibration by Ferry and Watson. This is very well established. I'm not going to go over it. From europium anomaly, we can get pressure estimates. It's less well established, so we compared 2 models, the one from Yakimchuk, which is a melting model. It gives us the, sorry, the areas in the colored area. And then we also use the tank calibration, which uses zircon europium anomaly and calibrated it against whole rock lanthanum-ytterbium ratios to get some pressure. We think the tank calibration is maybe a little bit too high because it doesn't really overlap with the Yakimchuk model. So we conservatively apply a 1 GPa decrease in that model. And the average value we use is the solid line that goes right through the Yakimchuk model. So we get some pressure estimate, which we consider is very conservative. We use that temperature and pressure to calculate TP values. And this is what the data looks like when we plot our 16 rims in it. So pressure versus temperature. The colored lines here are delineating the difference between what we consider high TP condition, intermediate TP condition, and low TP condition. And then in the background, you have those dashed lines, which are phase reaction limits. And the solid lines are areas where we would expect more eclogite, high pressure granulite, different phases. What you can see is the high FO2 rims right here in bright yellow only record high to intermediate TP values. The low FO2 rims record both high and low TP values. We did not make the step to go all the way to saying that this is a prograde or retrograde sequence because the ages overlap, and so we have no basis to make that claim, but it is not impossible. I'm just going to leave it there for you to think about. The importance of that result, though, is that the low FO2 rims all coexist at 3.35 GA. And the coexistence in those rims of both low TP and high TP is very typical of large-scale plate under thrusting. Okay, so let's put all of this together and look at the big picture image that is being painted by our result. I'm going to start with looking at the TP ratios, what we just discussed, as a function of time. The small points in the background come from this Brown and Johnson compilation. Those are whole rock values. And you can see that there is low and high TP at the same time when we know that there's clearly plate tectonics going on in Earth's history. Our data, the large samples, show that there is the same low and high TP conditions being recorded at the same time by the rims of our grains. And therefore, this argues that, or we use it to argue that there is already plate tectonic going on at 3.35 GA. We do not see the same correspondence coexistence in the Hadean, but it doesn't mean that plate tectonic was not active there. We just cannot argue as strongly for it. Our data allows it, it does not refute it. This is what is shown on the top now. At 3.35, we have both high FO2 and low FO2 with high TP and low TP values. This is very diagnostic of plate tectonics. At 3.9 GA, 4 GA, we have only high TP values and high FO2 values, and this could be either stagnant lid or mobile lid. We cannot tell. So if we compare our results, the proposed onset of mobile tectonic that our results indicates to other propositions that have been made in the past, we see that our results are in very good agreement with a lot of mostly recent works from 2020 onward, plus Bethan's in 2014. But it is significantly older than earlier estimates. So yeah, this is how we got to the title of our talk, Oxidized Hadean Magma and at least Archean onset of mobile lid tectonics. Final takeaway and then a teaser, and then I will be happy to take any question, and Shane is here to also help answer. We looked at the igneous cores of Jack Hill zircons, and we find constant uranium oxidation states in them, and these indicate near modern magma redox, FMQ plus or minus 1, at 4.1 billion years. We looked at the metamorphic rims of 16 of those grains, and they either are low FO2 or high FO2. Importantly, in those rims, at the same time, we have high and low TP values, which indicate mobile lid tectonic was active in the early Archean. The implications of our results, first, they challenge the notion that the early Earth had highly reduced magmas. We don't see any evidence for that. They support models that evoke an efficient mantle convection through the Hadean. I'm mentioning this because if you imagine that the Earth has to start very reduced, by 4.1 GA, the magmas at the surface, sorry, are already oxidized. And lastly, they require an onset of mobile lid tectonic before 3.35 GA. We've discussed this. Now, of course, if you have this new system, a new probe that we just discussed, you will want to ask, what about the rest of Earth history? I've told you about the Jack Hills, which are right here. I've told you about the calibration samples, which are in Shane's first paper. What happens at the GOE? This is something we're actively working on. I'm going to just show you a teaser of it, but we certainly see a change in the redox of the zircons across the GOE. There will be many more samples. This is just to keep you interested. So stay tuned. And I want to really acknowledge that this is the PhD work of Shane, who's done a remarkable job with the help of many collaborators, Mauricio being the lead one, Matt and Tony at APS, George Rossman at Caltech, and Bethan and Mark at UCLA. And this work was supported by Caltech, NSF, and Argonne. And I'll take any questions.
Thanks so much. Any questions, anybody? Oh,
I see Pound Valley is.
yeah, go ahead,
Go ahead,
John.
John.
It's a very nice talk, very intriguing results. I look forward to seeing more of it.
Thank
You've made an amazing number of tests on the validity of this, things that usually when people give a talk like this, they haven't thought about yet. Um, I'm wondering, have you done any experiments on zircons to try and oxidize them to see what conditions it would take to actually alter this signal?
That's a very good question. We have not been able to make such tests yet, but definitely yeah, actually we can do that in one of our next sessions. We haven't yet tackled it. Or maybe it's too early for questions about Zanes and
Well, maybe.
I'll ask another one then. The rims, the bright rims that appear to be metamorphic, have you been dating them also?
oh
You
yes, absolutely. Yeah.
sometimes see a billion year difference between the rim and the core.
Yes, they do, and actually, they in some of them there are that difference. You can see here, I didn't point it out, but the tie lines. The tie lines are the rim and core of the same grain. Um,
A lot of
Greg?
quiet. So do you know what the charge balance is for the difference of uranium-4 and uranium-6?
oh, what substitutes in its place? I can't recall. Maybe Shane, do you have that on the top of your head?
We don't have like a model for that, but we're, just with the amount of rare earth substitution in zircon, we're kind of assuming that it would be charge balanced that way.
Sure, yeah, it's
But
possible.
yes, that future work to try and model exactly how that charge substitution would work.
Looks like Greg has a question.
Yeah, this is amazing. I love it. Very thorough and very convincing. But I'm really impressed with how subtle the change is. Um, what is it compared to the GOE, for example?
Mhm.
What is the source of this oxidation? Is it photooxidation as we see on Mars? Or could that possibly be significant enough to even things out so much?
That's a very good question. So I'm showing you here less data than what we have yet, but we haven't written the paper, so I didn't want to put everything out there. One thing you can notice from that teaser data, though, is there's a lag between the GOE and what we see in the magma.
Right.
So a possible explanation is that you're oxidizing the surface, sending in sediment into the mantle, and you need a couple 100 million years to have that have an impact on magma generation. Um, we don't have a final answer yet, but this is one possibility.
But I guess I would have expected the GOE to be much more significant, more than three or four even. Um, cap delta FMQ, but it's not. Something is
Uh,
oxidizing the early planetesimals. Um,
I
presumably,
guess yes.
presumably that would be surface photooxidation mainly, I would guess.
One caveat. No, no, you're pointing something important. One caveat. Our Zane's oxybarometers has a limited range of applicability. It will work only from FMQ minus one, if I remember properly, to FMQ plus three, 3.5.
Yeah,
If you're
yeah.
below minus one, it will look like minus one. If you're above, it will look like three. So if you measure something at FMQ plus three, like we have one sample there, it
Right,
might be higher. We can't tell.
right. No, this is fantastic. It's a whole new world. Thanks so much.
Thank you.
Paul,
Uh, Paul, go ahead.
Well, the seafloor, which was being subducted, was still anoxic long after the GOE.
The seafloor, yes, but if there is any sediment that our hypothesis would be if there is any oxidized sediment that is being recycled as well, that would have an impact.
Hey, friends, I have two questions. Maybe I ask them separately.
Go for it.
So first, why you say mobile lead tectonics rather than plate tectonics? Do you have any evidence one way or another?
Um, Partly because if we say plate tectonics, we feel the pushback is going to be harder. Um, just yeah, to be more descriptive, stagnant versus mobile, being the way that we describe it. Maybe Shane has a better answer than me on this.
Generally, yeah, I think that it depends on who you ask, but the term plate tectonics has a lot of other implications that come along with it as far as like, is this a continuous network of plate boundaries and was this consistently operating? And so I think mobile lid is just a bit more general of a term to say the plates were moving around horizontally and bumping into each other. And that's what I think we have solid evidence for.
Thanks. And second question, a bit out of my expertise, but something I was exposed recently. So the redox state for magmas, like in arcs versus mid-ocean ridges versus oceanic plateau, are very different, like much
Yeah.
higher in arcs. And so it's one aspect. And second, like people observed for a while that Archean granites show a high oxidation state, and were recently papers arguing that Archean porphyry deposits highly oxidized, and try to explain it by a sort of um, breaking down of water and incorporation of hydrogen into peroxide, sort of without sort of oxidized sediments
Mhm.
or ocean flow going down. What are your thoughts on it?
I don't have any thoughts on it because I haven't looked at that. Can you? I'll have to check it. Maybe
Yeah.
Shin has thought more about it, but this is taking me unprepared.
Okay.
I'm actually not aware of that model either, but I'd love if you could send the paper over.
Yeah, it's I can dig it out, but it's Menk, and I think with Jeremy Rickards, and it's maybe Nature Geoscience, like
Okay,
2017 or something. But I can dig it out.
thank you.
there any other question, or should we thank Francois for such a great talk?
Thank you, everyone.
Thanks, Francois.
Thank you.
Really cool stuff.
My pleasure, and really keep Shane in mind because this is his hard work.
Good work, Shane. Nice. All right, so everyone, we'll see
Thank you.
next week. So take care till then.
Bye, everyone. Thank you, Paul. Thank you, John.
Bye.